Okay, welcome Math 31s. Today we're going to do trig review. We're going to do it not just sum and difference, but we're going to do all the different types of trig identities that you guys learned in Math 30. So remember something from our unit circle. Uh, so again, we have our first quadrant, and we would have these special triangles that we created, and we knew that this one was pi over 6, which is 30 degrees. We don't usually use degrees in calculus anymore. Everything next year when you do this in post-secondary will be in radians. And we would have root 3 over 2 and 1/2. Then we would have this one, which is pi over 4, or 45 degrees, which is root 2 over 2, root 2 over 2. And then over here at pi over 3, which is 60 degrees, we would have 1/2 and root 3 over 2. Up here we have 90 degrees, or pi over 2, and we know that this coordinate, because it's on our unit circle, is 0, 1. And I guess I could mention this one, 1, 0. And so we use this unit circle to either help us solve to find an exact value ratio or to find an angle. So I have both here. So if you are asked to find sine at pi over 4, sine at pi over 4, which is 45 degrees, is in quadrant 1, and we know that sine at pi over 4 equals root 2 over 2. Cos, however, at 5 pi over 6, remember that is over here with a reference angle of pi over 6. And when I'm over here in this quadrant, based on my cast rule, cos is negative. So cos at 5 pi over 6, we know based on quadrant 1 with a reference angle at pi over 6, cos is root 3 over 2, so it's negative root 3 over 2 because we are in quadrant 2. We could also do the opposite. We could be given the ratio and asked to find what angle it is. And this is where we would do 3 steps. We would do our cast rule to find out where is sine positive. Sine is positive in quadrants 1 and 2. Then I would find my reference angle. And if it doesn't give us a domain in terms of radians and degrees, we always default to radians. We know based on my unit circle that sine is 1/2 with a reference angle at pi over 6. And so what are my actual angles? In quadrant 1, x equals pi over 6. And quadrant 2, 5 pi over 6. And that's all you do. So that basically is lesson 6.1 in your chapter book, in your textbook. Then sum and difference identity, 6.2. So we have these to sometimes pull expressions together, like the one that's here, because we don't have special values for 50 or 80. They're not one of our special triangles. So instead what we do is we go to our formula sheet, which I'll post online, and we recognize that this is a sum or difference of sign. Because it's a minus sign, it's going to be the one that is a minus b. And when you get to post-secondary, you don't get formula sheets, just a heads up. So if you were writing an exam for me in this class instead of online, you wouldn't actually have all these formulas with you. So just a heads up for next year. So then I know my two angles A and B are 50 and 80. So I would write it as 50 minus 80. And I would get negative 30. And then I know what sine is at 30 degrees or negative 30 degrees. And I can actually go one step further and I can solve this. Next up is our double angle and Pythagorean identities. These ones are the ones we use more commonly. Something like this one, the 2 cos squared of 3x. You would want to recognize that that's a double angle, and it's cos of 2x. So all I do is I write it as cos 2 times whatever my angle is on the inside, and this can be written as cos of 6x. The second one, again, you're looking at your tan identities on your formula sheet. And we would recognize that this one is tan of 2a. So all we do is we take our angle and we multiply it by 2. And we get tan at pi over 4. Again, this can be solved. We know it equals 1 if we wanted to do that. This is just simplifying it or expressing it as a single trig function, so cos of 6x or tan at pi over 4. And so that's how our double angle identities worked. The next part we're going to talk about is proving identities. This isn't something that we're going to do in calculus, but I'm just going to review it. To prove an identity, you simplify everything to one trig expression usually, or as simple as you can go so the left side matches the right side. A lot of times you will be looking to factor, especially if it has an exponent of 3 or 4. Whenever you have something squared, you might want to use a Pythagorean identity or a quotient identity, which is those reciprocals. So remember, secant belongs to cos, so it's the same thing as cos squared, or 1 over cos squared. Sum and difference, which we just talked about, and double angles we talked about. Replace everything, so we write it as sine or cosine is usually a good call. So we'll just do an easy one. Prove that 1 plus cos of x equals sine squared x over 1 minus cos x. We obviously want to check this right side because it's the more complicated side. So we set it up as left side and right side. We write out what that left side is and what that right side is. And then I want to look for something, some type of identity. Whenever you have something squared, that's usually a good call. So this one right here can be written using our sine squared x plus cos squared x equals 1, which is our basic Pythagorean identity. We can now solve for sine x and write it as 1 minus cos squared x. So when I do that and I replace it, I recognize, well, it's got an exponent of 2, so I can factor it. It's a difference of squares. I get 1 plus cos x, 1 minus cos x, all over that 1 minus cos x. And you can see that these two cancel. I'm left with 1 plus cos x, and my left side equals my right side. We can also talk a little bit about restrictions. Right here, this is in the denominator. So 1 minus cos x can't equal 0. So cos x can't equal 1. Well, where does cos x equal 1? That's going to happen at 0 or 2 pi. It's negative 1 at pi. So we can say that x can't equal 0 or 2 pi. That would also be 4 pi, 5 pi, so we can say 2 pi n when n is an integer if we wanted to state it in general. And so that's a restriction. Those restrictions will come into play when we start to do our curve sketching of trig functions, which won't be till next week or the week after. The last section is solving. So this is 6.5. So we basically have done the entire chapter 6, which I will obviously give you guys some time to work through and practice. And we'll review this stuff as we start to do limits and derivatives of trig. So don't stress if you're not following some of the proofs or some of the solving, because we will go through it with each example that we do. So solving something like this, you're usually given a domain. If you're not given a domain, we solve it in general, so that's usually where we use that n as an integer. All I want to do right here, using this equation, is get my sign all by itself. So I'm going to move that root through to the other side, and then I'm going to divide by 2. And now we go through those same 3 steps: cast rule, reference angle, actual angle. So based on my cast rule, when is sine negative? Quadrant 3 and 4. What is my reference angle? Well, again, I know my unit circle. I know that sine is root 3 over 2 at pi over 3. And then I do my actual angle. What does that mean for x? Well, in quadrant 3, we're going to get 4 pi over 3. And in quadrant 4, we're going to get 5 pi over 3. And those are our two solutions in this domain. We could do one that involves factoring. So here you can see that we have a sine squared that's common to both terms. So I'm just going to factor out my sine squared x. I'm left with cos x minus 1 equals 0. What that means is sine squared x equals 0, or sine x equals 0 if I square root both sides, and cos x equals 1. So where does sine equal 0? Well, that's going to happen at 0, pi, 2 pi. It's included in my domain, so those would be my three solutions for that one. And then where does cos equal positive 1? Sorry, where does cos equal positive 1? That happens at 0 and 2 pi. So we can just state that our answers are 0, pi, and 2 pi for this equation. Now, sometimes you will have to replace using your identities. This is where you want to try to write something all in sine, all in cosine. So I have two options here. I could replace this sine squared and write it as 1 minus cos squared, or I can replace this cos squared and write it as 1 minus sine squared. First off, I'm just going to bring everything to the left side. And make it equal to 0. Just like we solved quadratics and solved everything in 30-1, we like one side to always equal 0. From there, I'm going to choose to replace this one. Again, that's not the only option here because they are both squared. I'm going to write this as 2 sine squared x plus 1 minus 2. And in my bracket, I'm going to write it as my 1 minus sine squared x equals 0. From here, I'm going to expand my bracket. I'm going to get 2 sine squared x plus 1 minus 2 plus 2 sine squared x equals 0. We have like terms now, 2 sine squared x, 2 sine squared x. So we get 4 sine squared x. Right here we get 1 minus 2, which is minus 1, equals 0. And now we have a difference of squares. We're going to get 2 sine x minus 1, 2 sine x plus 1 equals 0. Make each bracket equal to 0 and solve. And we are finding when x is equal to 1/2 and negative 1/2. That's going to be in all four quadrants. My reference angle is pi over 6. We're in all four quadrants. So my answers are going to be x equals quadrant 1, pi over 6. Quadrant 2, 5 pi over 6. Quadrant 3, 7 pi over 6. And then 11 pi over 6. And quadrant 4. And those are my four solutions. And that is as far as we are going to go in terms of review for trigonometry. So you will have some time to do some practice questions and review on your own before we start our limits and our derivatives, which we will do starting next week.